All right. Good morning, folks. Hopefully, you guys had a good day yesterday. I didn't see anyone come by or um, to get any extra help with this. So, let's hope then that you guys are getting this. I'm going to give you a chance to practice this. So, I'm going to assign set B for homework tonight, and it'll be due, and then you'll have tomorrow to work on it, and then it'll be due on Wednesday. I'm sorry, hold on one second. Let me go ahead and start my time here. And I'm sorry, it'll be due on Thursday, so that if you do have any questions with drawing these structures here, please come by and see me tomorrow after the exam and get some help with it. Okay. But after we finish up with today, whoops, let me after we go ahead and finish up with the structure today, we will go ahead then and I'm sorry, we'll go ahead and you should be able to work through the homework for this weekend. Okay, so what I'd like to do then is I want to go ahead and finish up with this discussion with the coordinate covalent bond, and then give you an opportunity to practice it tonight and tomorrow. If you need any help, come by and get that extra help. Okay, all right. So yesterday we left off. I asked you to show me how you would obtain the structure for the ammonium ion. Okay, so let's go ahead and let's take a look at the ammonium ion. Let me open up a whiteboard here, and let's take a look at how we would construct the ammonium ion. Now, understand the ammonium ion. Understand that we now have three different types of bonds that we can choose from to connect these atoms together. So hopefully you remember the formula for ammonium. And so what you should expect then is either on a quiz or on the exam for this chapter, I will give you the formula for the particular molecular compound, and you'll be asked then to write the structure for it. Okay, so with ammonium, I think with this particular molecule here, I should be able just to give you the name, and hopefully you should be able to memorize it. Okay? All right, so with ammonium here, what you're going to notice then is that we will have 5 different atoms tied together. Okay, so let's go ahead and like I did before, let's write out the Lewis dot structure for each one of these atoms here. Okay, so we have then hydrogen, 2, 3, and this is a positively charged atom. So you're going to notice then that one of those hydrogen atoms is going to be a positively charged atom, because what it has done is it's going to give up its electron, and as a result then we have a positive hydrogen atom here. Now if you're interested in this, then come by and see me. But if you notice that this positive charge, the whole molecule here, the whole ammonium molecule, and recognize, and we'll talk about it a little bit more in just a moment, the ammonium ions and all polyatomic ions are molecular compounds. How do we know that they're molecular compounds? The compound itself is made up of only non-metal atoms. Okay, we only have non-metals in there. And we said then that with compounds in which you only have non-metals, then it is going to be a molecular compound. What we're saying here then is these molecular compounds are charged. And so we're going to see why it's charged here. Okay, so let's say for right now, let's go back and let's say that you did not know that. And so we're going to write down 4 hydrogen atoms and 1 nitrogen. Okay, all right. Hopefully you see here that nitrogen has to be the center atom. It can't be hydrogen. Remember, hydrogen can only form single bonds. And so you can see then that 3 of the hydrogens, and it's going to arbitrarily pick these 3, they will surround the nitrogen, and they will form a bond with that nitrogen. And if we leave it only at that, okay, then we have the ammonia molecule, okay, the neutral version of that. Okay. All right. So we still have this one hydrogen here. Okay, so let's go ahead and let's take that hydrogen and let's write it in here. Okay. So you can imagine that the hydrogen comes in right there. Okay. Now at this point then, there is no bond that we know of that is made up of 3 electrons. It's either going to be a pair, 2 electrons, 2 pairs, 4 electrons, or 3 pairs with the 6 electrons. We have 3 here. There is no bond that forms, no covalent bond that forms that involves the sharing of 3. So what has to happen here is this hydrogen has to lose that electron. And that's why I was telling you that in order for this to happen, this hydrogen here has to first lose that electron. And remember, it loses that electron not just into the air, but it loses that electron to some other compound, polyatomic ion, for example, or it could lose it to some anion, but it loses that and it becomes this ion right here. Okay? And so now, if you can imagine, this hydrogen ion comes in. Okay? This hydrogen ion comes in right here. So this process has to happen. Okay? This has to happen right here in order to form the hydrogen ion. Okay, and so now how can a bond form here? It's going to be a coordinate covalent bond in which the nitrogen donates both of those electrons to that hydrogen ion to make that bond happen. Okay, so there it is, and there is your positive charge that we have with ammonium. Okay, so there's your positive charge. Now we know then how ammonium forms. Okay, and we can go ahead and we can see then that if we write down, if we summarize this molecule here, we have then 4 single bonds, okay? One of which, and I'm going to put this parenthetically, one of which is a coordinate covalent bond. And like I was telling you yesterday, a coordinate covalent bond is not a 4th category of bond. It just represents then what we do with the coordinate covalent bond is we show then how 2 atoms can be attracted to one another, 2 atoms can be bonded to one another, and only one of the atoms contributes the electron. Okay? So we know then that ammonium does have 4 single bonds, and we'll talk about how we know this empirically, what data we have to suggest this. I'll talk about that in just a moment, but that is how the ammonium ion forms, and that is how then polyatomic ions form as well. And we'll talk about these polyatomic ions again in just a moment. Okay? So go ahead and please compare your work to what we did here. Let's see how close your work was to what we have here. And if you have any questions on how this ammonium ion forms, please make sure you come by and you see me and get that extra help tomorrow. Or I will be available after school today. So please come on by and get your questions answered as well. Okay. All right. So let me go ahead then. So that's the ammonium ion. Let's go ahead and let's take a look at the rest of this here. Okay. All right, so we saw how carbon monoxide, one of the bonds in the triple bond was a coordinate covalent bond. Here we saw with ammonium ion, one of the single bonds, one of the 4 single bonds is also a coordinate covalent bond. Okay? So with that said, then the coordinate covalent bond is not a separate type of bond itself, but it's just a way that we can represent a bond in which only one of the atoms of the pair contributes the electrons to form the bond. Okay, and so with that said, then it is not a and I want to make sure you understand this. It's not a special type of covalent bond. It can either replace a single bond, a double bond, or one of the 2 in the double bond, or one of the 3 in a triple bond. Okay, but the key here then is that one of the atoms contributes both of the electrons. The electron pair comes from only one of the bonding atoms. Okay? All right, so now we can go ahead. Let's take a look at number 6 here in your problem set. I did ask you to do this. I think it was yesterday or the day before, and I told you, let's hold off on this and let's talk about double coordinate covalent bonds first, and then we'll go ahead and we'll deal and then we'll do this. Okay. All right. So we did hydrogen cyanide already. I'm not going to do that again for you. If you wanted to see it, make sure you come by and get that extra help. But I did that for you already. Check back in your notes and then see that. But let's take a look at sulfur dioxide and the nitrate anion. Okay, let me go ahead and open up a whiteboard here. Let's take a look at those 2 ions. I'm sorry, those 2 molecules. Let's see how they form. Okay, let's start out with sulfur dioxide. Okay, sulfur dioxide. Okay, so let's list really quickly what we have here. Sulfur is, oh, sorry, let me do this again. Sulfur then is, let's draw the Lewis dot structure for sulfur. Okay, sulfur is 2 pairs, 2 unpaired. Oxygen is exactly the same. 2 pairs, 2 unpaired. Okay. All right, there are the puzzle pieces. Hopefully you recognize here that sulfur, now it's going to be difficult for you here. I mean, I recognize these, I've done this long enough. But if you're not quite sure which atom is going to be the center atom, that is the atom which the other atom is going to be attached to, it's going to be trial and error. You're just going to have to give it a shot and see which one works. And when I say works, that means that all atoms involved have their 8 electrons. Now, if you put oxygen in the middle and you don't get that, And remember, all three of these atoms have to be bonded together somehow, either with a single bond, double bond, or triple bond, but they have to be bonded to each other. And when they are bonded to each other, every single atom must have their 8. And that's the criteria you use then to determine whether you have the correct structure or not. Okay, so let's go ahead and do this. I know this, so I'm just going to go ahead and I'm going to put sulfur as the center atom here. Okay, so sulfur is our center atom, and I'm going to write it this way right here. Okay, so there it is. There are the 6 valence electrons. And then I'm going to go ahead and I'm going to put oxygen, one oxygen over here, because sulfur is going to be the center atom. Okay, and one oxygen on this side here. Okay, so I have an oxygen on the left and oxygen on the right. Now, if you can imagine then this should be the easy connection to make. Okay, you can connect those two and those two together. So we have a double bond here. So let's go ahead and label this. We have one double bond. So this is a double bond right here. So a double bond forms between sulfur and the oxygen on the left-hand side. Okay, so that's what we have right there. If we leave it that way, folks, if we leave it that way, oxygen here will have, this oxygen will have its 8 electrons. There it is, it's octet, it's stable. This sulfur here also has its octet, and it is also stable at this point. But sulfur dioxide requires that all 3 of those atoms be bonded to each other. In this case, then, sulfur monoxide meets the criteria for sulfur and oxygen. This oxygen on the right-hand side here is left out in the cold. Okay, so what's going to happen here? I think you can imagine this happening then. Okay? I'm just going to move this really quickly here. Okay? And you're going to see that, whoops, sorry. And we're going to move that down. You're going to see then, and I'll tell you why we can do that in just a moment. Okay? So if we see this then, the bond that forms here is going to be a coordinate covalent bond right there, where sulfur contributes a single atom. Okay, I'm sorry, sulfur contributes both electrons to this single bond. Okay, so this is a single bond right here. It's not, we don't call it a coordinate covalent bond. Again, there's no single coordinate. That's what I get for walking and trying to chew gum at the same time. Writing and talking at the same time doesn't quite work. So this is a single bond, but the single bond formed because it's one atom, sulfur here, contributes both. So this is a coordinate covalent bond that happens to also be a single bond. Okay, all right. So with that said, then sulfur still has its 8, but in contributing those now, this oxygen that is now bonded to the rest of the molecule also has its 8. Okay, all right. So if you were to summarize this this molecule here, okay, you would say then that this molecule has one double bond. Okay, it has one single bond, and I'll put an asterisk next to this one because that single bond is a coordinate covalent bond, and the only way you can recognize that is by drawing out the structure here. Okay, and then it has then 1, 2, 3, 4, 5, 6 lone pair electrons. 6 lone pairs. I don't know, 1, 2, 3, 4, 5, 6. Okay. All right. So that's how we can describe this molecule right here, sulfur dioxide. Okay. All right. Let's go ahead then, and I will save this for you. Let's take a look at nitrate, the nitrate anion. Okay. So here we have another anion. This is a polyatomic anion. Okay. This is a molecule that is charged. So let's go ahead then and let's write out the pieces of the puzzle there. So we have then nitrate, nitrogen, sorry. Okay. We have oxygen, and we have 3 of them. Okay. 2. And then we will see then how all 4 of those pieces will fit together to form the nitrate ion. Now, if you notice, this molecule then has an extra electron, because this negative charge here, okay, means then that there's an extra electron that comes from the outside. Let's see how that works. Okay? All right, so because I know this, okay, and I'm going to write in, nitrogen is going to be the center atom. The oxygens will be situated around the nitrogen, and I'm going to write it this way here. Okay. Okay. All right, so there are the 3 oxygens. Okay. So again, if I draw it that way, is there, hopefully you see then that you can have this double bond forming right here. So you have a double bond, You have one double bond forming, so that's a double bond forming between the nitrogen and the oxygen on the right-hand side. Okay, so now at this point, then this oxygen has its 8. It's stable. Let's go ahead and write that in. So this has its 8 electrons already. Now we have to tie these two together. Okay, if you notice here, there are 3 electrons. Now you can say this. Let's go ahead and try this here. Okay, you can say then that a single bond forms right here. That looks like that could happen right there. Single bond forms right there. Okay, but at this point then, okay, this oxygen and the nitrogen has its 8. So the nitrogen now, by forming that bond, has its 8 electrons. Okay? This oxygen has not been bonded to nitrogen yet, and this oxygen only has 7. Okay? Now let's imagine what happens here, similar to what you saw with sulfur dioxide. Let's imagine then a coordinate covalent bond forms right here. Okay, so that we see then that electron, none of the electrons from the oxygen is used up at all. And then we have this bond formed right there. And that's going to be a single bond. So this is going to be a single bond. And I'm going to put an asterisk by this again, because this is a single bond that results from a coordinate covalent interaction, coordinate covalent bond here, in which the 2 electrons come only from the nitrogen. So with that done, okay, this oxygen now has its 8 electrons. So nitrogen still has its 8, 2, 4, 6, 8. This oxygen on the right still has its 8. And now the question is, this oxygen over here, it only has 7. It only has 7. But remember, there's an extra electron. This is nitrate. Okay? And so therefore, you can imagine then that there will be an electron. And I'm just going to draw this here right now. Okay, but remember, there's no such thing as floating electrons. Imagine this electron comes from another atom or another cation somewhere. Okay, so it comes in, and the oxygen there picks up that electron. And when it does so, look at what happens now. This oxygen now also has 8 electrons. And there it is. That's the nitrate anion. Okay, so the nitrate anion then is made up of 1 double bond, okay, 2 single bonds, and again, one of those single bonds is formed as a result of a coordinate covalent interaction here. That's this one right here, and this is another single bond here. Sorry, we got a single bond here. Okay, and we have then 1, 2, 3, 4, 5, 6, 7, 8 lone pairs. Okay, let me go 1, 2, 3, 4, 5, 6, 7, 8. Okay, yep, and that's it. And so that is how we summarize then the nitrate anion. Okay. All right, so you got to practice this, folks. This is something you got to practice doing. And again, with this here, and especially when we start talking about structure and we start talking about 3-dimensional structure, you really do not have time to write out all of these atoms on the side here, the Lewis dot structure. You should be able just to write it out and then start linking them together. And then hopefully at some point you can start using the dash lines instead of kind of using the bubbling here. Okay. All right. So you got to you got to practice this. Okay? And so with that said, set B for this for tonight and for Wednesday should help you with it. Okay. All right. So let's go ahead then. And whoops, I hope I saved that one. Let me go back quickly. Let me save that one. Okay. Okay, so again, take a look at hydrogen cyanide. We did that already. Come by and see me if you still need help with that. Okay, so with that said, then polyatomic ions then are simply molecular compounds that have either, all the atoms together have either given up an electron, and the only example we have of a molecular compound that'll do that is the ammonium. Ammonium is the only polyatomic cation. All the other atoms that, all the other polyatomic ions then are negatively charged. So they are polyatomic anions. And so therefore, all the other polyatomic ions will gain a charge very much in the same way that nitrate that we just saw gained a charge there. Okay? All right, so that's how, and so remember, with the polyatomic ions, you want to make sure you treat it as a single unit that shares that one charge. Okay. All right, let's go ahead and let's take a look at one more example. Okay, let's take a look at number 7 in your problem set. What I would like you to do then is draw out the structure for the, this is the sulfite anion. Draw out the structure for the sulfite ion, and let's see what you come up with. Okay, so go ahead and get that done, and then we'll compare answers. Okay? Take about 2 minutes to get that done. Okay, let's go ahead then and let's take a look at how you did this. I'm not going to draw out the Lewis dot structures anymore. Again, like I said, I want you to get to the point where you don't have to do so, but we want to be able to draw out the structures correctly. So please do practice that. Okay. All right. So sulfur then center atom. Okay. So I'm going to draw the Lewis dot structure for sulfur, and I'm going to place that at the center. Oxygens then will be on the sides. Okay. I'm going to draw like this. We have 1, 2, and I'm going to draw this one on top. 3. Okay, so there are our 3 options. All right. I think the obvious connection that you can make here then is going to be, I think, this bond here and that bond there. So I'm going to start drawing this. So we have a double bond here. So hopefully you recognize that. So we have 1 double bond. Okay. All right. Now, with that said, then let's go ahead and let's take a look at what else we can do here. Okay, so we have then a let's say we have a coordinate covalent bond that forms right here. Okay, so let's go ahead and do this. Therefore, then this electron is not being used, so it will just pair up here again. And so we have then here, okay, a coordinate covalent bond that forms there. So we have a single bond there. Let's go ahead and write that in. All right. And then we can do the same thing here. Let's say then that this this bond here also is a coordinate covalent bond. So therefore, both of these oxygens contribute nothing. So we have 2 coordinate covalent bonds right there. Okay. And so we have another single, I'm sorry, I don't put an asterisk right here as well, just to remind us that this is a coordinate covalent single bond, and this is another coordinate covalent single bond. Okay, right here as well, put the asterisk there. Now, if you drew the structure this way, right here, you're going to look at this and say, hey, well, I'm done. Look at this. This is great. I have 8 electrons here. I have 8 electrons here. This atom here has 8 electrons, 2, 4, 6, 8. And then we have 2, 4, 6, 8. Sulfur has 8 electrons as well. We're done. We're done. We have a stable structure. Everything is good. And then you look at this like, oh, there's a 2 negative charge here. So this isn't the correct structure. What we've done here is we've written out the structure for the neutral compound that is known as sulfur trioxide. Okay, so this compound does exist. Obviously, we drew the structure here, but that is not sulfite. Because to be sulfite, to be the sulfide anion, we need 2 more electrons, and there's nowhere we can put it here. Okay? So this is a perfect example of how you're going to work things out. And initially, and this is going to happen a lot, especially when you start doing the homework for tonight. Okay, you're going to run into issues like this. Okay, and that's okay. What do you do then? You go back to the drawing board. Let's go back to the drawing board, and we start over. Okay, and let's go ahead then, and let's take a look at it. Okay, all right. Let's go ahead then and let's draw our sulfur again. So sulfur will be the center atom again. So let's draw that. Sulfur, center atom. Oh, sorry. Okay. And again, I'm going to draw the oxygens so that, okay. And this time I'm going to shift that right here. And I'm going to shift this last one. And I'm going to keep that one right there. Okay. All right. Now let's do this instead. Okay. We can single bond right there. Another single bond right there. So we have 2 single bonds. So we have a single bond here. Okay. We have a single bond here. And these are not coordinate covalent bonds. These are single bonds that are formed with 2 electrons, 1 from each of these atoms. Okay. And then over here, then we will form a coordinate covalent bond. Okay. So let's go ahead and let's just shift this electron down to here. Okay. So we have then a coordinate covalent bond that forms right there, which is a 3rd single bond. So it is another single bond, but this single bond is different from the other 2. because this single bond here is a coordinate covalent bond. So I'm going to put an asterisk by that one. Okay. All right. Let's count electrons here. Let's count electrons and let's see what we have. Okay. We need 8. Sulfur here has its 8. So sulfur is happy. It has its 8. This oxygen here has its 8 as well. This oxygen here has only 7 electrons. And this oxygen here has only 7. And so you stop and you think to yourself, wait a second. How can this structure work where you have 3 single bonds that bond all 4 of these atoms together? Okay. Well, remember, you got to make space for these 2 electrons here. So you can imagine then, folks, that now 2 electrons will come in. 2 electrons will come in from another atom, for another one. One will come here, and a second one can come right there. Okay. And as soon as that happens, there it is. This octet is complete for both of these atoms here. And now we have accounted for the 8 electrons. And all of the atoms now are stable. So to summarize this molecule here, then, we have then 3 single bonds. 3 single bonds. Okay. And again, one of them is a coordinate covalent bond. And we have then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lone pairs. 10 lone pair electrons. Okay. And so there it is. That is the structure for the sulfite anion. Okay. All right. And so that's how we go about doing this. It's going to take trial and error first, folks. It's going to be trial and error. And that's how we work through this. Okay. Now, there is another structure that looks like it will also meet up with the criteria there. And I'm going to draw it for you right here. So we have then sulfur. Okay. Okay. Not as the center atom here. It's going to have a single bond here with oxygen. Okay. So we have that one right there. Okay. And this oxygen here, and let's go do this here, is going to be bonded, a single bond to this oxygen here. It's going to have 1, 2, 3, 4. Okay. You have a single bond right here as well. Okay. So, and then the last oxygen is going to be bonded. Oh, sorry, wrong one. To the sulfur. So sulfur, it kind of serves as a center atom. We have 2 center atoms here. We have sulfur, and then we have this oxygen here. Okay. And so we have then this last oxygen out here. And we have a 3rd single bond right there. Okay. So no coordinate covalent bonds needed. No coordinate covalent bonds needed. Okay. And furthermore, this structure also has room to accommodate 2 extra electrons. One right here, okay, and the second one will fall in right there. So that way, then all atoms now, and so let's draw that in. There it is, and there that is. So all atoms now have their 8. And this is a valid structure. This also has 3 single bonds, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we also have 10 lone pairs here. 2 structures that look that meet up with all the criteria. 8 electrons for each atom. It has space for the 2 extra electrons here. And so which one of these is the correct structure for sulfite? How do we go about determining then how, if we have 2 equally valid structures that meet up with all the criteria that we've discussed so far, okay, how do we know then which one is going to be the correct structure for the molecule sulfite here? It comes down to we have to have data. We have to have empirical data. We have to have empirical data to support the bond. Okay. And what is this empirical data that we can use this here? What we refer to as bond energy and two, bond length. Because only one of these 2 structures here will have the correct bond energy and the bond length here. Okay. Basically, what we do then is the bond energy. We'll talk about this. Okay. It is the energy needed to break a bond. Okay. So bond energy is the energy needed to break a bond. So for example, to break the sulfur oxygen bond here, it's going to take a certain amount of energy. Okay. So it's going to take a certain amount of energy to break those bonds there, and then it takes a different amount of energy to break the oxygen bond. Okay. So for our molecule down here, we have the 3 sulfur oxygen single bond. Okay, so they're all the same. Now, with that said, remember, even though this is a coordinate covalent bond, it is still a single bond. Okay, here, so we have here all three of these bonds, single bonds, are identical to one another. Here we have we have two sulfur oxygen bonds and one oxygen oxygen single bond. So they're not the same. We have different types of bonding there that will have different bond energies, and we have different bond lengths. And so what we can do then is we can use that to collect the bond energy and bond length to support that. Okay, so understand then, here we have three single bonds, here we have three single bonds, but here we have three sulfur oxygen single bonds. They're all the same. Here we have two sulfur oxygen bonds and one oxygen oxygen bond. This structure right here is the one that is supported by this empirical data. So let's go ahead then and let's take a look at what this empirical data is. What are bond lengths and what are bond energies? Okay, so let's go ahead and let me save this for you. This here. Let's take a look at that. Okay. So bond length then, let's talk about bond energy first. So the bond energy, and let me make sure you understand this. We're using this data here. We can collect this data. We can, there are ways that we can collect and determine then this bond strength here. This unit here is known as kilojoules per mole, okay? And this is in picomoles. That is the distance between those two atoms. Let's take a look at what the bond strength is first, and we can discuss and we can measure that bond strength in what are called bond dissociation energy. Okay. So the bond strength is, so this here, what we refer to as the bond strength is what is referred to as the bond dissociation energy, meaning exactly what I just said then, is that it is the energy needed to break these bonds here. So it's going to take a certain amount of energy to separate those two and break this oxygen-oxygen bond. And the energy that is needed is what is 498 kilojoules per mole. So kJ over moles, okay, is referred to as kilojoules, okay, per mole of molecule. Now, you know what kilo means, that's 1,000. Joules is the unit of energy, and we'll talk about what this unit of moles, we'll talk about what this unit of mole is in chapter 10. Okay, but that's what we have here. This is the unit of energy, 1,000 units of this energy here for every 1 mole, and it's a quantity unit of oxygen. So it's going to take then that much energy to break it up. So if you notice here, if you compare that to this bond here, which is the oxygen-oxygen single bond, which only has a bond energy of 213 kilojoules per mole, you see then that the single bond, the single oxygen-oxygen bond, is weaker. It takes less energy to break that. That's what that bond association energy tells us. Okay? So if it takes less energy to break this bond, the oxygen-oxygen bond is weaker than the oxygen-oxygen double bond. If you compare then the nitrogens here, the nitrogen-nitrogen triple bond, it takes 945 kilojoules of energy to break that, compared to the nitrogen-nitrogen single bond, which only takes 275 kilojoules of energy. Okay, so we can use this bond dissociation energy, which again, we can measure this. We can measure this energy here, and we can use that to determine then whether we have the right bonding interaction or not. So what we've done here, what we have been doing up to this point, we've been drawing the structures as if it was an arbitrary thing. We just do it. No. The way that we know that this is actually a double bond here between oxygen and oxygen is because we have to record that data. We have to have empirical data. We have to have supporting data for the models that we draw. Okay. All right. So bond dissociation energy is one of the pieces of evidence that we use to support our molecular structures, the structures that we've been drawing up until this point. So, I think up until this point, when I've taught this in the past, some students have been wondering, they wondered, oh, this seems very arbitrary. It seems like we can just make any type of connections, but the answer is not true. We have to be able to support what we do here. Okay. All right, so let me go ahead then and share with you the, and so bond length here also, let me go ahead and share this with you. If you notice then, the bond length is the distance between, or the length of the bond. The way you want to think about it is the distance between the atoms here. So with the oxygen-oxygen double bond, the bond length is 121. PM is picometers, okay? And the bond length for the oxygen-oxygen single bond is 148 picometers. So the oxygen-oxygen double bond is closer together. It brings the two atoms closer together, and it's a stronger bond. The oxygen-oxygen single bond is further away, okay, and it is a weaker atom. And if you take a look at the nitrogen triple bond versus the nitrogen single bond, you see the exact same thing here. The nitrogen-nitrogen triple bond brings the atoms closer together. The nitrogen-nitrogen single bond allows the atoms to stretch out further. Okay? And so the summary that we can make here then is that the stronger the bond is, the stronger the bonding interaction is, the closer those atoms are going to be to one another. Okay? That's what we see here. And so what I would like to do tomorrow, what I'd like to for tomorrow's lesson on Wednesday, I want to continue talking about this, and then I want to use this to show them why certain structures that we draw are more valid than the other ones. Again, going back to what we did in the previous slide, we had two structures for sulfite, and I'm going to share with you the data the data table in just a moment. Okay, and I'm sorry, tomorrow. Okay, and you're going to see then that based on that data, we know then that one of those structures for sulfite is correct, and the other one cannot be correct. Okay, all right. So what we'll do then is we will pick up with this discussion on Wednesday. So please, so the video lesson on Wednesday will cover this this bond dissociation energy and bond length, how we use that to confirm our structures that we draw. Okay. All right. Very good, folks. I will see you folks in class. I guess Thursday then. But like I said, please stop by tomorrow after examine if you have any questions about this here. Okay. All right. If not, I will see you folks on Thursday. Okay. Bye.